So let's review 2.2, and this will be a nice segue into the same activities that we're performing for your solution, right? You have a function. So you have this logic gate diagram or a function. You have to derive the truth table. Once you derive the truth table, you can come up with the canonical expression. Once you have the canonical expression, it's easier to do the logic statement. Once you have the logic statement, well, then you go into the HDL environment, and all the pieces of the puzzle are together and they're close to alignment, and you're like, oh, this isn't so hard. If you don't, a student did ask on Friday, and I'm very glad that this individual asked, do I have to do the other stuff? And I said, oh, absolutely. If you don't do the truth table, then do the canonical expression, then do the logic statement before you get into the HDL. You're going to miss something. That's just how it is. Okay, so we'll walk through this very quickly. And then what I'll do is stop sharing and stop recording. And basically, if you would like to share your screen about what you have to date, and you'd like some quick assistance, we'll use the rest of the class to assist, okay? So here we go. So for each problem, create the truth table and then compile the canonical expressions for each Boolean function. So here you see I have two inputs, which means I have a truth table that has two inputs, a two-input truth table template. Because I have a not in the mix, I have to apply the not first, because in terms of mathematical order of operations, I have to compute that. And then I'm going to AND that result with B in order to get my output. So my first step is to come up with a completed truth table, which has 0, 0, 1, 1, 0, 1, 0, 1 for A and B. And then I add a column in the middle, and I not these values for A, and that gives me 1, 1, 0, 0. It flips them. Any questions so far? Okay, so I AND this with this, and if any of the inputs are false, then the output is always false. When I have I have a false output here, I have a 0 output on both cases and a 0 output here. So this is the only case where they're both inputs are true. To do the canonical expression, I want to state the most efficiently what the output of this function is with the least number of expressions. And in this case, there's only one true, which means a standard canonical expression is what I want to do. And I'm not looking at the rendered output of the first operator, the not. I have to look at the original input. So A is false in this case, and B is true, which means my standard canonical expression is A tick B. Any questions so far? Hearing none, let's move right along. So here I have three inputs. I have a 3-input truth table template. And I know that according to the mathematical order of operations, I have to multiply and divide before I add and subtract, which means that the output of R and S has to be rendered before I can OR it with Q. Does everybody follow what I'm saying?
Yep.
So I inserted a column here and I used the R and S. And because I'm using AND, you'll notice that everywhere there's a 0, I only have 2 places where there's a true. And now I'm ready to OR it with the Q output, right? So I have the Q column right here. So if I OR Q with the output of R and S, because I'm using OR, that's the most permissive. So anytime I have any one at all, I have an output of 1. But I'm going to put it in this column right here in the final output column. So if I look at 0 and 0, no, that's a 0. A 0 and 0, no, that's a 0. A 0 and 0, no, that's a 0. A 0 and 1, that's a 1. A 1 and a 0 is a 1. A 1 and a 0 is a 1. A 1 and a 0 is a 1. A 1 and a 1 is certainly a 1. Which one is easier to state? 3 false or 5 true? How many expressions do you want to write? 3 or 5? 3 is correct. I'm going to write 3 reverse canonicals where the input values are listed in each case where the final output is 0 or false. So this is where it gets tricky because with the extra columns, you got to be careful. I have Q-tick, R-tick, S-tick. Do I have a volunteer to tell me what the next one is? Well, it's actually stated there. So Q-tick, R-tick, S, that's what we have here. And then we have Q-tick, I'm sorry, Q-tick, R, S-tick. So those ones kind of throw people off. That's my canonical expression. Now, here's the part where I want to impress upon you why you do the canonical before you derive your logic statement. You can have a logic statement that says, if Q is 0, R is 0, and S is 0, or if Q is 0, R is 0, and S is 1, or if Q is 0, R is 1, and S is 0, then output equals false, else output equals 1. You can create a logic statement like that. But why? I want to show you something really cool here. When you do the canonical expression, standard or reverse first, do you notice anything these 3 statements have in common? Are there any common values? Go ahead.
The Q value is always 0.
The Q value is always 0. Yes, that's a condition. So you have some variation there between the S's and you have some variation between the R's. But the simple truth is when Q is 0 and let's see, how else can we make this simple? And R is 0. Does it matter if S is 0 or 1? Let me ask the question again. Let's think about this. A logic statement is language. And it's a little different than algebra, but let's go through it again. Q is 0, regardless, right? And when R is 0, does it matter if S is 0 or 1 as far as getting a false outcome? No, it doesn't. So your logic statement can read what? When Q is 0 and R is 0, what? Out equals?
Yes, false.
Out equals
0.
0. And that takes care of both of these, right? And then you could say, or when R is true and S is 0, then out equals 0, else, all else, right? Output is 1, right? It's this last part right here. So that's why we encourage people to get the canonical expressions in front of them, because what you're looking for is a pattern here to make your life simple. I don't have to write out if Q is 0, R is 0, S is 0, or Q is 0, R is 0, S is 1, or Q is, I mean, I'm like, oh my gosh, why would your logic statement be so thorny? Keep it simple. Now, why would you care? The cleaner your logic statement comes, there will be rare cases where a software algorithm is actually more efficient than certain hardware combinations. What? Yep. And that leads to amazing innovation. Because at that point, you're like, wait a minute. I got a software algorithm. I got a logic statement for a software algorithm that's more efficient than the 15 logic gates that produce this result. So let's go back to the drawing board and look at this logic gate combination again. What am I saying? It's an iterative process, and you got to look at both sides of it. And having a grasp on the canonical expressions, both standard and reverse, has great value, because when you're creating your logic statement, you can simplify. And the shorter and simpler, the vastly more efficient. Let's say that again. The shorter and simpler, the vastly more efficient. Do you want to be known as the person who had to write 15 statements to do the same thing everybody else in the room took 3 statements to write? Oh, you got the job done. And as long as they're running it on like an Intel i9 processor, then okay, everybody's good. But sucks to be you if you're on a smaller machine, a lesser capable machine. Does everybody get what I'm saying here?
Yeah.
Okay. All right. Now those are subtle points that we normally engage in the 3rd module and then later on. But all right, let's keep going. This one. We have 3 inputs, which means we have a 3-input table. 3-input table is 2 to the 3rd. That means we have 8 sets of combinations. The original values are for V, W, and X, 4 zeros, 4 ones. There's the W, 2 zeros, 2 ones, 2 zeros, 2 1. There's the X, 0 1 0 1 0 1 0 1. Everybody see that pattern, right? That pattern still works. Now, what am I doing right here? Well, the first thing I have to do, which operator has to be taken care of first? In order of operations, which one has to be done first?
Multiplication.
Say again?
Multiplication.
Yes, but there's another one right before that.
Oh, the not.
The not, yeah. The ones you can see that are down here, that's the correct answer. And multiplication has to happen, but before that even, the not has to apply. So I have to take the X value and I have to work this first from this input. So instead of 0 1 0 1 0 1, what do I have? 1 0 1 0 1 0 1 0 1 0. Everybody got me?
Yeah.
Okay, we're good so far then. Now we're going to AND the output of this with this, right? So I'm going to take the, notice what I did, right? I color coded this. Now I'm taking the W with the X bar. That's why I color coded them, just to kind of keep them straight. So now I'm going to AND those. And that's where this column comes in, W and X bar. Well, essentially what I have is an AND. I mean, it looks complicated, but what's in the middle here is that I'm ANDing these 2 values. So I have a 0 and I have a 1. That's why it's a 0. Here I have a 1 and a 1, which is why I have a 1. Which one is easier to do? The standard canonical or the reverse canonical? Are we there yet? Are we there yet? No, we're not there yet. What else do we have to do yet?
Or
The OR.
yeah, the or.
I have the output from here and I have to do this with an OR, right? So let me OR these 2. 0 and 0 is 0.
Yeah.
0 and 0 is 0. 0 and 1 is 1, right? You follow it across 0, 0, 0, 1. I got a 1 here. I got a 1 here. I got a 1 here. Actually, as soon as I'm dealing with OR, when I see every 1, I know the answer over here is every 1. Does everybody understand what I'm telling you? Whenever OR happens, it's like an easy button. You're like, okay, wherever there's a 1, the output is a 1. I got 4 of them right there. Does everybody understand how we got it?
Yeah,
All right, now which one's easier to state for the output? Standard or reverse canonical?
Reverse canonical.
Reverse canonical is easier because there's only 3 zeros, but there's 5 ones. So I'm going to go reverse canonical again. And this time I have to take the original values of the V, the X, and the W. I'm not in that order though. For every case where there's a 0. So that's why here we have a V tick, W tick, X tick. That's easy. Next one, V tick, W tick, X. Everybody see how we got that? It's this last one that's different. It's like, okay, here's the rebel. V tick, W, X. Do I have a common element out of these 3 expressions?
the V.
Is 0.
When V is 0, right? When V is 0, and then just like we said before, look at this. And when W is 0, does it matter if X is 1 or 0? No, it doesn't matter. Yeah. So I want to do my logic statement. I have the same efficiency that comes into play, right? So when V is 0 and W is 0, output is 0. Or when V is 0 and W and X are true or 1, then output is 0. Otherwise, else, output is true, right? So everybody got what I'm saying?
Yeah,
Okay. I'm going to stop sharing and stop recording. You're welcome to stay in session and share a screen. If you'd like to do what we did Friday and basically just pop into view and say, hey, I want to share my truth table. Let's have a look. And then let's look at the canonicals. And then let's look at the logic statements, right? We go from there. Then you go to the HDL environment. And that's where the fun begins, because basically you can take these canonical expressions and test to see if your logic gate works. And it is so amazing when you get into that HDL environment and you're like, it works, oh my gosh, it works. This thing works. And that's when you pat yourself on the back and say, I just designed my first miniature computer chip. Because that's what you're doing on a crawl level. The next module we get to walk. Modules 4, 5, and 6, we're running and flying. Any questions?